Hi, this is Mrs. Basden, and today we're going to talk about weak acids, which is section 16.6. So a weak acid, by definition, is one that is only partially ionized in solution. So what that means is instead of it completely going to H plus and whatever the other part of the acid is, there is a mixture of the H plus, the other ion, and then the unionized acid in solution. So weak acids are in equilibrium. So when we show the dissociation of a weak acid or the ionization of a weak acid, you can see that it has a double arrow instead of when we write the dissociation of a strong acid, there's an arrow that's only going in one direction. So when you set up the Kc for a weak acid, we can actually now start calling this Ka specifically because it's for the dissociation of an acid. You can see that the K is set up the same way as it was before. So here's our weak acid, HA. So here's the dissociation of the HA, and you can see it splits up into H plus and A minus. And then when we set up the K expression, we could also call this Ka. We still take products over reactants and we raise them to the power of the coefficient. What you're going to see for most of these, for most of the acids that we look at, they're all going to be 1 to 1, but just pay attention and make sure that you remember that you still, if there is a coefficient there, you're going to raise it to that power. So like I said a minute ago, the equilibrium constant for these, for the weak acids, are called the acid dissociation constant, and that's notated with a Ka. Set up the same way as all the other Ks we've talked about, you just specify for these a Ka because it's for an acid. When you're comparing values of Kas, the larger the value of Ka, the stronger the acid. So you can see some examples here in the table. So here is hydrofluoric acid. We've talked about hydrofluoric acid a little bit in class. Hydrofluoric acid is a relatively strong weak acid because it has a much larger Ka value, and you can see as you go down here the values of the Ka decrease, which means they are weaker weak acids. So when you calculate a Ka for a weak acid, or you calculate the pH of a weak acid, it's a little different method than what we did before. So because there is not complete dissociation, you have to figure out what is left once equilibrium is achieved. So we have to go back and use our ice tables again. So when we look at these problems, there's going to be two different variations you're going to see. One of them is going to give you a pH or an H plus concentration and ask you to solve for the Ka of the weak acid. The other type is going to give you the Ka for the weak acid and then ask you for either the H plus concentration or the pH. So we're going to go through examples of both of these types, and then we're going to do a couple example problems with both of them. So this first one says to calculate the Ka from the pH. So they're giving us the pH of a 0.1 molar solution of formic acid, which is HCHO2, at 25 degrees is 2.38. And they want us to calculate the Ka for this acid at that temperature. So when you set up the dissociations for these, a lot of these are going to be acids that we don't recognize. First of all, the way to determine if this is a weak acid is that it's not one of your 7 strong acids. That's why it's important to know those 7 strong acids. So when you see something that is not one of those, then you know that that's your weak acid, one of your weak acids. So when you set up the dissociation for these weak acids, all you're doing is you're going to take the front H off. So this is your acid. When it dissociates, you get H plus, CHO2 minus. So then when you go to set up the Ka, you're still taking products over reactants raised to the power of the coefficients. Like we said, most of these are all going to be 1 to 1, but just double check and make sure that you always look for those in case those happen to be there as we get into some of the other ones that we do later on. So this is where this Ka came from. So that's the first thing you can do here. Once you do that, then we're going to use that pH to find the H plus. Now the pH comes from the H plus at equilibrium. So when we use our pH equations that we did the other day and we figure out what H plus is, we have to remember that that's the H plus for that acid at equilibrium. Okay, and that's going to take us to our ice table. So here's just a reminder of how we did this. So pH is the negative log of the H plus. You put in your 2.38, and then you end up with the H plus being 4.2 times 10 to the negative third. So again, that's a review of what we did a couple days ago. That's why we started with that. So then from there, we go to our ice table. So here's my formula again, or my problem again. It says the pH of this 0.1 molar solution is 2.38. That's how we got the H+. That's what we used on that previous slide to get our H+. Here's our dissociation that we wrote on the first page. And then we also know what our Ka, our equilibrium expression is, because we took the products over the reactants. Okay, so the information that comes from the problem, this 0.1 molar, that's our initial concentration. Like we said before, if they don't say anything about the products, then we assume that those are 0. This value here, this H+, we use as our equilibrium concentration of H+. Okay, so in the beginning, the only two things I have filled in are this and this. Okay, just like before, I use my equilibrium concentration to get my change, and then I use my stoichiometry of my equation to get everything else in the change column. Then I take that down to get my equilibrium. Okay, I know this looks kind of confusing that I drew all over it, but just a reminder here, one more time, this original goes here. That's my initial concentration of acid, and then I use the pH to get my equilibrium concentration of H+. I use my equilibrium concentration to get the change, fill in the change row by using the stoichiometry, and then just like before, I'm subtracting if it's a reactant and adding if it's a product. So then once I have my equilibrium values, those are the ones that then would go into my Ka expression that I'm going to show you on the next page here. Just something to notice here, this looks kind of weird because you're starting with 0.1 and you're ending with 0.1 in equilibrium. If we look and see how small this value is, 4.2 times 10 to the negative third, when I subtract that from 0.1, it's basically the same thing. When I round to my sig figs, it rounds back to 0.10. So don't be alarmed if you end up with the same thing. That's just because the number you subtracted was such a small number. Okay, so then these values here come from the equilibrium row on the last page. So this was my H+, this was my CHO2 minus, and this was my HCHO2. So these were all values taken from the equilibrium row, and then this gives me the value of the Ka. The other thing we can do is we can calculate percent ionization. So that tells us to what degree the acid has ionized or dissociated. So if you look at this, you're taking the H+ at equilibrium divided by the initial concentration of the acid. So it's showing what percent of that acid actually broke apart into H+. And then you multiply by 100 to get the percent. So in this example, my H+ at equilibrium was that 4.2 times 10 to the negative third. The initial concentration was 0.1. So for this one, my percent ionization was 4.2%. Okay, the other situation you're going to see is calculating pH from Ka. So for this one, it's going to give you the initial concentration of the acid, but it's not going to give us anything that can help us with an equilibrium concentration. So this is where we're going to have to use X's. We introduced this in the last chapter, but we didn't use it a whole lot. So this chapter, we're going to actually use it a lot more. So what they have to give you, though, is they have to give you a Ka for this situation. So if they want you to calculate the pH and they don't give you any of those equilibrium values, they have to give you the Ka. So in this case, they tell us the Ka for acetic acid is 1.8 times 10 to the. So the first thing we can do here is set up our Ka expression. So I'm still taking products over reactants from the dissociation that you saw on the previous page. From there, then I can set up an ice table. So this is my ice table, and again, it shows the dissociation, how the H+ comes off and you're left with the C2H3O2 minus. The initial concentration goes in the initial box on the ice table. They don't give us concentrations for any of the H+ or the C2H3O2 minus, so we assume those are 0. The other thing it doesn't give us here is that it does not give us any equilibrium values. So since we don't have any equilibrium values, we have to use X as our change. The X again corresponds to the coefficients. Since all of these are 1, it makes it easy. So it's minus X for the product or the reactant, and then plus X for each of the products. So at equilibrium then we have 0.3 minus X, X, and X. Now all of the ones that we're going to work with, we can assume that X will be very small. The general rule is X has to be 5% or less of the original concentration of the acid. Like you saw in that previous example, it ended up being the same. So we're going to assume that that X is small, so we're going to just use 0.3 for the equilibrium concentration of our acid. We still leave these X's in here though. Okay, so then once you do that, then we can calculate the X's. So this was our value that was given for the Ka. X was the value for each one of our products. 0.3 was our reactant. Then we can solve for x. And then so what that gives us is the x is equal to the H+. Now that we have the H+, now we can get the pH of the acid. So since x equals H+, we can sub in the value that we just solved for x, and then that gives us a pH of 2.64. Okay, so let's look at this. This is actually the same example that we looked at first, but we're going to go ahead and work through it just so you can see how this all works out. Okay, this is our ice table. So formic acid was HCHO2. So what we're doing here is we're going to break this into H+, CHO2 minus, and what we're trying to calculate here is the Ka. So we know that Ka is going to be concentration of H+ times CHO2 minus over HCHO2. So what we need is those equilibrium values so that we can plug those in so that we can then calculate the Ka. So what I know so far is I know the initial concentration is 0.10 molar. So I know the initial concentration is 0.10 molar, and the initial for these is going to be 0. The other thing it gives me is the pH. So I know that pH equals negative log of H+, so I can use that to solve for H+. So if I solve for H+, that ends up being 4.2 times 10 to the negative third. So that value goes down here, 4.2 times 10 to the negative third. Okay, once I have that, now I can use that to fill in my change column. So the difference between the 0 and the 4.2, I had to add 4.2 times 10 to the negative third. These are all 1 to 1, so this is also going to be 4.2. This is 2 over here, just to be clear. 4.2 times 10 to the negative third. And then this one is going to be minus 4.2 times 10 to the negative third. Okay, then I can go back and use those values to fill in my equilibrium. So 0.10 minus 4.2 times 10 to the negative 3 is still going to round to 0.10, so that's going to end up being the same. This one is 4.2 times 10 to the negative third. Then I take those values and substitute them in for my Ka. So I have 4.2 times 10 to the negative third times 4.2 times 10 to the negative third divided by 0.10. And that gives me a Ka of 1.8 times 10 to the negative 4. Okay, and just like last time, the Kas do not have units. So Ka here would be 1.8 times 10 to the negative 4. Okay, now let's look at one last example here. Now for this is one where they don't give us anything at equilibrium. So this one says we have HCN. So HCN is going to dissociate into H plus Cn minus. Okay, this is our ice table. And they tell us our initial concentration is 0.20. They don't give us any values for those, so we assume those are 0. They also give us a Ka value. So that's telling us that they're not going to give us anything in equilibrium. So this is one of the types of problems where you have to use the x's. So your change column here is going to be minus x plus x plus x. And then we use that to get our equilibrium. So this is going to be 0.2 minus x, x, and x. Okay, so when we set up our Ka expression, we know Ka is equal to 4.9 times 10 to the negative 10th, and that's going to be equal to the H plus times Cn minus over HCN. So then we can substitute our values in. So this is going to be x times x over 0.2, because we're going to assume that that x is small enough that it's not going to make a difference. So then we solve for x. So x ends up being 9.9 times 10 to the negative 6. Now this is a concentration, so this is molar. And then from that, we can get the pH. I can say the pH equals the negative log of 9.9 times 10 to the negative 6, which was my H plus value which gives me 5.00. And remember what we talked about with sig figs? We have to leave those 2 decimal places to have 2 sig figs. Last thing we want to look at here are things called polyprotic acids. Now, we're not going to deal with these a lot at this level, but a polyprotic acid is just an acid that has more than 1 proton. So if you look at the list, you can see these are H2s, or there's 1 H3 there. So when you have a polyprotic acid, each proton dissociation has its own Ka value. So if the difference between the Ka for the first and the next Ka values is 10 to the third or more, then we usually use the first Ka value to calculate the pH. Like I said, we're not going to deal with these a lot, but just so you realize that when you have a polyprotic acid, each dissociation has its own Ka value. So it loses one of those H's at a time.